Well, I hope you guys are feeling good. Um, and then so just the computational section of the midterm. That'll be due tonight. I hope that's going okay. I've been having office hours for this class on Mondays from 3 to 4. And then I've held office hours for my Stats 10 class on Wednesdays from 5 to 6, but I don't know, stats they haven't really been coming. So I'll open up that time to you guys as well. So if you want office hours from 5 to 6 on Wednesdays, you guys are welcome. What's that? Yeah, that I guess that includes today. I might not be able to answer all of your questions, but we'll see. Okay, so on Monday we left off, and I was confused by the behavior of the gradient descent algorithm. So I went home and I did everything out on paper, tried to compute everything, and the gradient descent algorithm that I had programmed was behaving exactly the way it was supposed to be. And so, it's known as kind of the steepest descent algorithm. So this is where we left off on Monday. We calculated this is our contour plot for different choices of B0 and B1, the intercept and the slope, okay, for just this very fictional data set of four data points. X is 1, 2, 3, 4, and Y is 2, 6, 4, 8. And we said, choose an initial intercept of -2, choose an initial slope of 1, and we will try to use the gradient descent algorithm. And it does approach the true value of 1 for the intercept and 1.6 for the slope. And it just looked like it has this funny behavior, right? I was expecting it to go in the direction of steepest descent, which I would think is tangential to our contour lines, and so I was worried, but it turns out this is the correct behavior. We even tried implementing it in matrix form, which is the way we're going to go. We'll expand on this. So in matrix form, we have our X matrix, which consists of values of 1 for the intercept coefficient, and our values of X for the slope coefficient. Okay, and so we can calculate the intercept, and using our slope, we can graph our contour lines. Okay, and so I'm going to, I'll put this in red. This is the results of the same gradient descent algorithm using matrix notation, and we can see it pretty much traces the exact same thing. So both algorithms are behaving the same way, whether we calculated, so the first method we calculated the partial derivatives, okay, and then and we created our gradients that way. In the second algorithm, we created a matrix and used the R's matrix notation to calculate our gradient and find that as well. Okay, so both of those behave exactly the same. And then I also there is a gradient descent algorithm programmed into the package animation. Okay, so you can load library animation. The funny thing is, or I guess the complex part is, you have to program the cost function. Okay, in terms of x and y. All right, and so in our case, we're going to define x as our intercept and y as our slope, okay? And then the function that we want to minimize as a function of our slope and intercept takes into account the data points that we have used, okay? So essentially, I am plugging in, the data point is the point, the first data point is the point 1, 2, okay? So the squared error is y minus the intercept minus 1 times the slope of y, okay? The second data point is the data point 2, 6, okay? So the amount of error is 6 minus the intercept x minus 2 times the slope. Does that make sense? And our third data point is the data point 3, 4. So it's 4 minus the intercept minus 3 times the slope, okay? So even though it says x and y, x is the intercept and y is the slope. And so I had to calculate our optimization function as this, and then you simplify it in terms of x and y. And that's the argument that you provide to the function gradient descent. So you have to provide it a function of x and y, and then this will work. Well, I just want to make sure this line's okay, or is anybody confused about this line? Okay. Well, that's great then. Okay. Okay, so I've programmed in this function, okay, which is essentially our cost function of error, okay, and then now I'm going to implement gradient descent. So this is a professionally written gradient descent algorithm, which we also know is true, and if we ask for it, it indeed behaves the same way using the animation that our thing did, okay? And at this point, it just gets all garbled and stuff, but indeed, it kind of bounces back and forth until it reaches kind of the center of this thing, okay? And it's still going, but and eventually it'll reach the optimum point of 1.6 here. Okay. I'll post this code is actually already posted up on CCLE, so you can download it and test it out yourself. Yes.
Did you choose to put the arrows on it, or?
That's a default setting of gradient descent. I know it's kind of it's a little annoying. Let's see if I can remove the arrows. Color.arrow. Okay, so I guess color.arrow I'll leave blank. White? How do I do this? All right, let's try this. Color.arrow equals white. Let's see if this works. No, it doesn't, because the entire arrow is now white. So this that doesn't work. I don't know how to get rid of the arrowheads. Okay. Yeah, I don't know how to get rid of the arrows. I know it looks ugly, but that's the animation package there. Okay. Okay, so we have a few things that we can do to gradient descent to kind of I don't know, improve its performance and whatnot. And let me see if I can actually find. There's another. Let me see, gradient descent, and it was quadratic bowl. Is what the okay, so here's an image of someone else's. How do I make this? How do I zoom in on this? Okay, and so our thing is kind of behaving this way, all right? And we can improve the performance of our gradient descent algorithm by doing what's known as feature scaling, okay? And so here, I'll plug in. So feature scaling, the big idea here is you're kind of like normalizing your x variables, okay? And so far we've just had one x variable, and the values of the x variable were 1, 2, 3, 4, okay? And so what feature scaling does is it normalizes those to kind of have a mean of 0 and a standard deviation of 1, or something in that order of magnitude. Okay, so I'll write this down. And so that makes our contour plots less elliptical and more round. Okay, so with gradient descent, we have what's called feature scaling. And this is, okay, so scale our x variables. So they have approximately mean equal to 0 and standard deviation equal to 1. Okay, so you know, our x and our y goes 1, 2, 3, 4, and 2, 6, 4, 8. Okay, and really our x matrix is consists of x0 and x1. x0 being our intercept. So these are just, we have 4 1s and then we have 1, 2, 3, 4. Okay, because everything in x0 is equal to 1, we can't scale that one. Okay, so x0 cannot be scaled. Okay, but x1 can be turned into basically a x1 scaled, which will be you know, basically x1 minus the mean of x1 divided by the standard deviation of x1. Okay, so something like this. Okay, and then so this will basically turn our matrix into 1, 1, 1, 1, and then we'll have something else here. Okay, so some negative and some positive values. Okay, and this is especially important when we, if you're going to use gradient descent for something that's highly multidimensional. Okay, so gradient descent, it's a pretty good algorithm. So even if you have like n-dimensional data, so if you know x, so here x is just one dimension. But x could have 5 columns or 7 columns of data or whatever, you know, n columns of data. And gradient descent is a good way to arrive at an optimum value without the need to you know, search the entire parameter space, okay? So, I don't know what this is, so let me just find the mean of 1 through 4 is going to be 2.5, and the standard deviation of 1 through 4 is this. So I can just say 1 through 4 minus 2.5 divided by standard deviation of 1 through 4. Okay, so I would get something like minus 1.16 minus 0.387, positive 0.387, and positive 1.16. Okay, something like this, and then we will use this to optimize our to find our optimum values. Okay, so so using Andrews-Ing's notation, instead of betas, we've got thetas, but theta is going to be theta 0 our intercept, and theta 1 our slope. Okay, so let's try this out. So how did I do this? Okay, so making our matrix X, this is our original matrix, okay? Oops. And I'm just gonna implement our cost function, our gradient function. Okay, so to create our scale data, all I'm gonna do is just make a copy of X. So if we ask what X scaled is, it's just currently our same as our copy of X, but I'm going to replace the second column of X by saying, subtract off the mean and divide by the standard deviation. Okay, and then so if I look at the new scaled, our X dot scaled, we've got exactly what we have here. Okay, and so we can regress Y onto X. Okay, we can just say, what's the linear model of Y regressed onto X scaled? Okay, really just the second column, because, or I can say do it on all of X, but don't give me an intercept. Okay, and it will tell me that if I use this, the intercept is 5 and the slope is 2.0656. Okay. We can also go for it using what is that? X transpose X inverse times X transpose Y, and that will also give us the same coefficients, right? So because linear regression is a solved problem. Okay, we can. So we implement the optimization algorithm, and I just want you to see the difference here. Okay, so if I create our contour lines, they're much more roundish. Okay. And actually, I think these are currently not on the same scale. So let's see. If I went from -2 to 5, this might even look more round. Okay. So so here I have a range of 7 and a range of 7 up on the top and the bottom. And because I know the answer, I kind of know where to kind of center the picture here. But we can see this contour plot looks a lot more circular, right? So you know, one thing of feature scaling. So you know, the contour plot when data is not scaled could look something like this, where you have these very skinny ellipse type things, okay? And then our search over, my picture sucks. And you know, our search might take a while to, because it's bouncing around, and then finally it gets to here and it goes down the middle, okay? You know, with feature scaling, the contour plots are a lot more round. Man, it is really hard to draw circles. Come on. Okay, and then your search will go kind of a lot nicer. Okay. That's kind of the idea. So we can do this, and let's see how it goes. All right, so here we go. We'll do our theta matrix, or we'll optimize theta, and it seems to have found the thing quite quickly. Wait, that's not what I want. Okay. Where did I start? I started out at 3, -2. 1, 2, 3. Wait a second. 2, 9, 3, -2. Where's 2? Let's just plot this again. Okay, yeah. So if I start down here, we can see just the path that it takes to get to our center is very quick and direct. Okay. All right, and we can also kind of take a look at kind of the performance, like how quickly does it converge to our optimal solution here. Okay, so you know, another graph is we can ask how quickly does the algorithm converge to an optimum solution. Okay, and so we can create a graph where on the x-axis is the number of iterations, and on the vertical axis we've got kind of our cost function. So for linear regression, this would be total error. Okay, and so you know, wherever you start, you're going to have lots of error, and the idea is after a few after a few iterations, the amount of error drops. Okay, but then you start getting to a kind of a point where the amount of improvements that you get gets less and less and less, until it kind of reaches this asymptotic level. Okay, So this could be, you know, one algorithm. And then another algorithm could, maybe it's slower to converge, okay? So it starts off here, but, you know, with each iteration, the amount of improvement that it gets is much less. And eventually it gets, whoops, kind of to this asymptotic level, but it's taken a lot longer to get there, right? Okay, so, you know, over here, you know, we got good solution here, and then over here, you know, good solution much later. Okay, and so by drawing this graph, this can kind of give us an idea of how much better one algorithm is compared to another. Okay, it also can give us an idea of how aggressive we can be with our learning rate alpha. Okay, so if I pick a huge learning rate alpha, I get the problem where you know, I diverge from the optimum solution. Okay, you know, so again, selecting alpha, our learning rate, so too large will lead to divergence, and too small will just lead to slow convergence. Okay, and so we can create a graph of the total error as a function of the iterations, and just see, kind of get an idea of our performance, and we can see, you know, how would choosing different values of alpha affect this. Okay, so we'll try this. We'll first try it with the non-scaled version of our algorithm here. Okay, so I'm going to create okay, so I have a cost function that just says basically take our current parameters, theta 0 and theta 1, you know, multiply that by x, subtract off the value of y, square that, and add them up. That's our cost function. This is the thing that we want to minimize, right? So this is our cost function, and then so all I'm going to do is in our loop, I'm going to create a new matrix called cost history. Okay, and it's just going to have one column in there. And cost history, oops, at location I is just going to be the cost of x, y, and theta. Okay, and that's all I'm doing. So all I'm doing is I'm just going to create a new matrix of cost history. Oops. And we'll see its performance here. So let me just make sure I've got this x and y. Theta is that. Let me just get rid of everything here. Okay, and I'll post this up here. Okay, so this is without our scaled data. So So we'll ask for theta, and then we'll just ask for our current cost history. We'll ask for the tail of this. Okay, and so we could see that it has done well. So I'll just plot kind of cost history, and we'll say type equals L. Okay, and so we can see the cost. It starts high and then it drops off quite quickly, and it seems to converge. I'd say after about 50 iterations, the improvement is only quite small. Okay, so let's just take a look at after 50 iterations. Let's see. Oops. Okay. I mean that's fairly significant. Okay. Okay, so we're down to about a cost of 7.4 by 50 iterations, and a cost of 7.21 by 100, and a cost of 7.20 by iteration 150. Okay, we can do the same thing. Okay, this time using the scaled algorithm, and I'm just going to add that one line that says throw in our cost history. Keep track of this. All right, so starting off again, so same algorithm, x scaled. Okay, and let's take a look at oh, I've done something wrong here. Okay, there we go. I get it. Let me run that again. Okay, so here nothing's improved in the last second. So, okay, so take a mental snapshot of this image, and let's just plot cost history. Okay, and what do we see? We see it has kind of the rate at which it converges is a lot faster. So it seems by cost history, location, I don't know, 15, or maybe, okay, by the 20th iteration, it's down to 7.27, and by the 30th iteration, yeah, it's down to 7.20. So we can see, and by the 40th iteration, we are much better than we were when we had the other algorithm. So, at the 100th iteration and the 150th iteration, we've surpassed the performance of the other one, basically, with just I don't know, 1/3 of the iterations here. Okay, so we can see scaling our data definitely helps us out, and we can also see just kind of how changing alpha affects this thing. Okay, so I'm just gonna create kind of cost history 2, and we will update this, and here I'm gonna just alter my alpha to something a little bit bigger, okay, like 0.03, and we'll see. Okay, let's see how picking a slightly bigger alpha affects this. Let me choose another color. Shoot. Oh, 1 through 200. Is that right? Oh, No, I screwed that up. Okay, so we have that. Okay, so we could see the blue line declines a little bit faster there. Okay, and that's just bumping it from 0.25 to 0.03. I'm afraid if I bump it up too much, we're going to run into a problem where it diverges. So I've bumped it up to 0.05, and we'll see what happens here. Okay, so 0.05 is working, and we can see it's dropping even faster. I'm going to reduce my number of iterations to something like 40, okay? Just so we can kind of zoom in into this location here. So this is our original 0.025, whoops. I lost my spot. Do this. Okay, so that's there we have that. So now I'm going to bump this up to 0.05, and we'll plot this. Darn it. Keep making the same mistakes. Okay, so that's at 0.05. Let's say what happens if I bump it up to 0.15. Here I'll do a green. Okay, so at 0.15 we're still okay, and it's converging very quickly. If I do 0.5, I fear something bad will happen, but I don't know. I don't know. Well, I don't know. Yeah. Okay, so with alpha too large, we could see the it's diverging quite a bit. We're at 10 to the 39th power. So at 0.15 we were okay, but at at 0.5 we're not. So there's just a point where you kind of push it a little bit too much, and yeah, so 0.2 is no good. Wait, so at 0.15 we're okay. Let's see, 0.19. 0.19's okay. I don't know. So you can kind of just play around and see what happens. But the idea is, we can always adjust alpha and plot kind of the performance of our algorithm against the number of iterations here. Okay. And this was just a simple example with unidimensional x. But once we have it in matrix form, we can generalize it to incorporate multivariate x. Okay, so I'll post this code up. I've posted up the gradient descent code. Please take the time to look through the code. Make sure you understand the steps that kind of the code is doing. So. So you kind of get a feel for how gradient descent works. It's a well-known algorithm, so it's implemented professionally in a lot of packages and things like that. But I think just kind of seeing it, handwritten out is also helpful. So, okay, we'll see you guys on Friday.